All right, let's move into the second part of our notes on 5.3. So in the first part, in video number 1, we just talked about all these different methods for factoring here, and we learned grouping and then sums and differences of cubes. And now we're moving on into what we were really trying to do in 5.3, which is to solve polynomial equations that are of a little bit higher degree than what we were used to in Chapter 4, where everything was quadratic. So let's dive into our first example. Now, I did just want to clarify here, our directions, I should be a little bit more specific than what I wrote the first time. We're going to try to find all of either the real or imaginary roots of each one of these polynomial equations. And if you remember from that big, long slide of notes we took in 5.2, roots are basically just solutions to your polynomial equations. So here we go, guys. We've got 2x cubed minus 5x squared is equal to 3x. The first thing I want you guys to notice is that we are dealing with a cubic polynomial equation here, because the degree here, the highest power that we see on our variable, is 3. And one thing, I'm kind of stealing some content from the end of the chapter here, guys, but I think it's worthwhile to go ahead and talk about right now. One big idea we want to get across is that if you're dealing with a third degree polynomial, we should expect to find a grand total of 3 roots. Now, some of them are going to be real numbers, some of them might be imaginary numbers, and the other thing I got to warn you about, some of them could be what we call double roots, but I will get to that a little bit later. Okay. So we're going to solve this by factoring. And the first step to factoring, if it's not already done for you, get your polynomial set equal to 0. So we're going to subtract this 3x from both the left and the right side here, and that should cancel out. And that'll leave us with a 2x cubed and a minus 5x squared, and then a minus 3x is equal to 0. None of those are like terms, so none of them combined. And we're just going to start doing now the same thing that we did in Chapter 4. We're going to try to start factoring this expression on the left-hand side and then utilize the zero product property. Now, the factoring in Chapter 5 is going to be a little bit more complicated than it was in Chapter 4, but the same basic ideas are right. Step number 1, everybody, is to always look for a GCF that you can pull out if possible. And looking at these 3 terms, 2, 5, and 3 don't have a common factor other than 1, but I am able to pull out an x. And I know that doesn't seem very significant, but it actually makes this problem a ton easier. You'll see why in a second. Pulling out that x now, we're going to have a 2x squared and a minus 5x, and then just a constant now, minus 3 left over. Okay, and now from here, what's going on? We now have ourselves this expression left over in the parentheses, which I'm hoping we know the name of. It's a quadratic trinomial. So the second thing I'm going to try to do here, guys, is to factor that quadratic trinomial by reverse FOIL. This is the kind of factoring we did a whole bunch of in the middle of Chapter 4. So let's try to split that big trinomial into the product of 2 binomials, and let's see what we can do. We're going to split the 2x squared up into a 2x times a 1x. Looking at this sign right here, it's a negative. That tells me that this sign and this sign right here are going to be opposites of one another. One is a plus and one is a minus, and I really don't know which it is right now. So I'm going to go ahead and take a guess, and just to prove a point to you guys, I'm going to try to guess wrong on purpose. I would go minus plus right here, okay? And we're going to have to test our answer to find out if we guess right. Now, I need a number that goes here and here, and those 2 numbers need to multiply here to 3. Well, 3 is a prime number, everybody. That's not going to work. So let's see what happens if I put a 3 right here and a 1 right here. Now, that was a total shot in the dark. I took 2 complete guesses. I did minus plus rather than plus minus, and I did 3, 1 rather than 1, 3. So I've got to test this now to find out if we guessed right. And just about always, guys, the first product, 2x times x, is going to equal your first product there. And your last product, negative 3 times positive 1, is going to equal this. But the real test, let me get rid of that junk here, is when you do outer and inner, trying to see if they equal this negative 5x. So my outer product there is a plus 2x. My inner product is a minus 3x. Those combine to a negative x, not what I needed right here. So what does that tell me? I guessed wrong. Not surprising. That's going to happen more often than not. So now you've got to go back and change something that you guessed. And let's see, I guessed 3 and then 1. I'm going to change the order now and make that a 1 and a 3. Let's see what that does for us. Now our outer product, 2x times 3, is a positive 6x. And our inner product, negative 1 times x, is a negative x. And when I add those up, I get a positive 5x. almost what I was looking for here, but I wanted it to be negative. So remembering something from chapter 4, when you get the right size term there, but just the wrong sign, all that means is that your signs were backwards, everybody. So I'm going to erase my minus and then my plus right here and make that a plus and then a minus, and I think I should be good to go. Real quick, that is now a negative 6x, and that is a plus 1x, and those combine into the negative 5x that we needed right there. So it took some guessing and some checking and a little bit of revising, but we now have this thing fully and correctly factored. Now, where are we going next? We're going to use the zero product property, which says that let me write this off to the side right here, that A times B will equal 0 if either A is 0 or if B is 0. Although in this case, we actually have 1, 2, 3 factors right here. So this is kind of A times B times C will equal 0 if A is 0 or B is 0 or C is 0. So what do we do, guys? We take each of these 3 factors, we set them equal to 0, and we solve them to find our roots. So I'm hoping you guys can skip this step pretty soon, but we would take x minus 3, set it equal to 0, and solve by adding 3 on both sides, and we'll get x equals 3. That's one of our roots, one of our solutions. This one's a little bit tougher to do in your head. 2x plus 1, we set it equal to 0, and we would solve that first by subtracting 1 from each side. 2x then is equal to negative 1, and then, let me go ahead and shrink this down a little, guys, sorry, and then, okay, we would divide both sides by 2, wrong button, here we go, divide that by 2, and we get x equals negative 1 divided by 2 is just a negative 1/2. There's your second root. And this is the one out in front that people need a little practice at. Let me repeat what I said a moment ago. You take each factor, set it equal to 0, and then solve for x. So I'll do that now. I take this factor, which is just plain old x, I set it equal to 0, and I solve. Except that one is already solved. So x equals 0 is one of our 3 roots to this polynomial equation. And as we said a while ago here, guys, we were expecting, because this was a 3rd degree polynomial, 3 roots. And sure enough, we found 1, and 2, and 3, and they all appear anyway to work. Now, if we wanted to check this, we could plug those values in for each one of them. Real quick, if I plugged a 0 in here, you'll notice that all of these terms contain a factor of x. So that would be 0 minus 0 equals 0. Yeah, that one's pretty quick and easy to see. How about x equals 3? Let's think about that one here. Let's see, 3 cubed is 27, and 27 times 2, that makes a 54. Minus 3 squared is 9, times 5 is a 45, should equal 3 times x. Well, 3 times 3 is 9. Yeah, 54 minus 45 is 9, so we end up with 9 equals 9, and that one works out as well. This third root that we came up with right here, so that one worked. This third one of negative 1/2 is a little bit tougher to see, but I'm going to ask you guys to trust me on that one. So yeah, that's how we do it, guys. So it's really the same process we were doing back in chapter 4 when we were doing quadratic trinomials, but now the degree of difficulty has just gone up a little bit. And as we said a while ago, we expected 3 roots, and sure enough, we found all 3 of them. All right, that's our first equation solving problem, guys, when we were dealing with a cubic polynomial. Let's take a look at a second one right here. All right, what do we have now? 3x to the 4th plus 12x squared and equals 15x cubed. Now, what I notice right here, guys, the degree of this polynomial is 4. We're dealing with a quartic polynomial equation right here. That means that we should end up with a grand total of 4 roots because our power, our degree, is 4 here as well. All right, let's try to do this the same way we did the last one. Step 1, get it equal to 0. So I'm going to subtract the 15x cubed, and I'll have to cram that in between right here because I would like this to be in the right order. And we're going to end up with 3x to the 4th minus 15x cubed and a plus 12x squared, all of which is equal to 0. Guys, I can't stress this enough. Everything we do in these problems is predicated on the zero product property, which only works if your right side is 0. So you've got to bring that other term to the other side. There's no point in factoring or doing anything else unless you've done that. Okay, just like before, let's look for a GCF. 3, 15, and 12 are all divisible by 3, and we've got 4x's, 3x's, 2x's here. That means we can pull out 2 of them. So 3x squared is our greatest common factor, and now we start a big set of parentheses. From 3x to the 4th, pulling out a 3x squared, we're left with just an x squared. And then a minus. 15 divided by 3 is 5. We had 3 x's. We pulled out 2, so there's 1 x left. And from the third term now, this is going to be a plus. 12 divided by 3 will be 4. There were 2 x's. We pulled both of them out, so there are no x's left on this last term right here. And this is where we are after we've pulled out our GCF. Now, just like in the previous problem, having done that, I think there's a really good chance that this quadratic trinomial is going to factor. So let's give that a shot. If it doesn't, you guys aren't going to like what we're going to have to do. I'll get to that a little bit later. All right, so looking like this, guys, all that equals 0. Here we go. How do we split up x squared? X times x. Signs are maybe a little bit easier this time. This plus right here tells me that these two signs are both the same, and then I look right here to find out that they are both negative. So minus, minus, and we need 2 numbers now, guys, that multiply to 4, and because the signs are the same and both of your coefficients here are 1, they're going to have to add up to 5. So how do you split up 4? 2 and 2 would add up to 4, not 5, but 1 and 4 are the 2 numbers we're looking for. Let's check that real quick. Outer product is a minus 4x. Inner product here is a minus 1x. Put those 2 together, and sure enough, there's your negative 5x that we needed. Okay, so we got the factoring right and complete, guys. That's as far as we can go. So now we'll use the zero product property. We will take each factor, such as 3x squared, set it equal to 0, and solve. Well, what are we going to do here? This is a little more complicated than just the x we had before. We would divide both sides by 3 and get x squared is equal to 0. Oh, and then we'll take the square root of both sides and we'll get x equals, well, the square root of 0 is 0. That, everybody, is your first root to this equation, and I'll come back and say more about that in just a second. Now our second factor right here, x minus 1, we would set that equal to 0, bring the 1 to the other side, and get x equals positive 1. Got it. And our third and final factor right now, we'll set x minus 4 equal to 0 and solve, add a 4 to both sides, and we'll get x equals 4. Now, right there, guys, that's everything that we've come up with. Those are all of the roots of this equation here that we were able to find. But if we go back to what we said at the very beginning of this problem, because this was a 4th degree polynomial, we should have expected to find 4 roots. And it sure looks like we only found 3. Well, the key to that, everybody, relies on a concept we talked about in section 5.2, the concept of multiplicity. Multiplicity, if you recall, is the number of times each root or each zero occurs. And with this 0 we got right here, this root x equals 4, that factor only occurred 1 time. So our multiplicity right here was equal to 1. Same thing happened with the x minus 1. That only occurs once, so the multiplicity is 1. But in the first solution that we came up with, we had an x squared right here, guys. And so if x squared was equal to 0, that tells us right there that our multiplicity here was equal to 2. So it's really the sum of the multiplicities of all of your roots that should equal your degree. So we got 2 plus 1 plus 1. That's the 4 that we were looking for. Now, real quick, if I wanted to be thorough about this here, guys, if we were to graph this polynomial really, really fast, and I'm going to be pretty sloppy and inaccurate about this, guys, what do we have? We have a root of 1. That's going to be 1 x-intercept. We have another one at 4, and we have one at 0. So this graph is going to touch the x-axis at 0, and again at 1, and again at 4. Now, if I look at what we're dealing with right here, guys, this is a positive 4th degree function. So our end behavior is going to take us up on the left and also up on the right. So that tells me that this graph is going to do this over here on the left and also kind of the same thing over here on the right. So what does it do in between? Well, at x equals 0, we're starting right off with the interesting one, the multiplicity is 2, which is even. That means that the graph does not cross the x-axis at x equals 0, but rather it just bounces off it. So it's going to bounce up, okay, and back into the first quadrant. Then it's going to turn around and hit the x-axis at 1, where our multiplicity is odd. So at that point, it's going to bust through the x-axis and then at some point turn around and hit the x-axis again at 4. And again, the multiplicity is odd there, 1, so this graph crosses through the x-axis at 4, and this is actually a pretty decent representation for what our graph for this polynomial function looks like. So just wanted to take that opportunity to talk to you guys a little bit more about multiplicity. Okay, that's how we handle example B. 3 more for you guys. All right, x to the 4th minus 3x squared is equal to 4. First step is the same as always. Get this thing equal to 0. So anything on the right, I'm going to move over to the left. X to the 4th minus 3x squared, and then a minus 4 is equal to 0. Now, I'm sorry, I jumped the gun right here. We're dealing with a 4th degree polynomial, which means we should see a grand total of 4 roots, or at least the sum of their multiplicities should be 4. Now, when we go to factor this one, this example is unlike A and B, which we did just a second ago. In both of those cases, there was a GCF, a greatest common factor that we can pull out. Here, there isn't one. There's no number you can take out from 1 and 3 and 4, and because this last term is a constant, no variables, you can't pull any x's out either. So we'll make a little note right here, guys. There is no GCF right here of what you can pull out. But I want you guys to get familiar with what it is that we're dealing with right here. This is kind of a weird and special case. We're dealing with a trinomial on the left-hand side, and it is quartic, because our degree is 4. But unlike a lot of other quartics, this is a weird one. Your degrees right here, guys, we have x to the 4th, and then x to the 2nd, and then a constant right here. No x's at all. And when that happens, when your degrees go 4 and then 2 and then 0, we can essentially then, all right, we looked for a GCF. Now what we can do, I know this looks a little bit weird, is go straight to reverse FOIL. We can factor this thing, as it is right now, into the product of 2 binomials. But it's going to be a little bit different than what you might have seen before. Let's take a look. Our first term right here is x to the 4th. So we need a term that goes here and a term that goes here that when we multiply them together will give us a product of x to the 4th. Now it could be x to the 4th times 1. That multiplies to x to the 4th, but that would be pretty unlikely. It could be x cubed times x. But what's unlikely about that, there are no x cubed or x to the 1st power terms in this polynomial, so I highly doubt it's that. It is, in all likelihood, the most reasonable thing, probably the first thing you would assume, x to the 4th is most likely going to split up into x squared multiplied by x squared. Now let's just keep going with this. Remember, guys, factoring is really a matter of guessing, but then we have to check and make sure we've got it right. Next thing I would worry about are my signs, and that minus right there tells me that these two signs are different. One is a plus, one is a minus. And now I need two numbers here that multiply to -4 and combine right here to -3. All right, so it looks like what's going to work right here, guys, is a -4 and a +1. -4 plus 1. Let's double check this and make sure we got it right. This is new for us. First product, guys, x squared times x squared is x to the 4th. Outer product is a -4x squared. Inner product is a +1x squared. And then our last product here and here is a -4. Well, as is very often the case, those two terms in the middle combine, and we end up with x to the 4th minus 3x squared minus 4, which is exactly the polynomial expression we were trying to get it to equal to. So, good news, guys. Took a little bit of doing, but we factored this one correctly. So, this is a weird example of a quartic trinomial that can really be dealt with as if it were a quadratic. Okay, so the factoring is, okay, you can kind of do this two different ways. I'm really going to tell you guys that the factoring is not quite completely done. Although even if you missed what I'm about to show you, if you're sharp, you can still get this problem completely correct. Let's see if we can go any further. X squared plus 1, guys, this is what we would call right here a sum of squares. It doesn't factor any further than it is. That has to stay x squared plus 1. But maybe I jogged your memory right here. X squared minus 4 is a difference of squares. That's a perfect square. That's a perfect square, and they're being subtracted. So a difference of squares factors into the product of two conjugate binomials. What times what is going to give us x squared? X times x. The signs, when you're factoring a difference of squares, are always 1 plus and 1 minus. And what is the square root of 4? That's going to be a 2. So the x plus 2, x minus 2, those are the last two remaining factors. And with where we are right now, nothing factors further. So now we're ready. I'm going to switch to my purple pen right here. Now we're ready to use the zero product property and get our roots. Right here, guys? If you need to do this on paper, you can, but maybe you can do it in your head. You set x minus 2 equal to 0, add 2 to the other side, and you'll get x equals 2. There is our first root. Right here, you'd set x plus 2 equal to 0 and solve by subtracting 2 from both sides and get x equals negative 2. There is your second root. And now we take this factor right here. I'm going to write this one out for sure. X squared plus 1, set it equal to 0, and solve. Well, there's only one x in this little equation here, guys, so we're just going to use inverse operations, even though it's quadratic. I'll subtract the 1 from both sides and get x squared is equal to negative 1. I would undo a square with a square root on both the left and the right. And the square root of x squared is going to be x. The square root of negative 1, I'm hoping you guys remember from the end of chapter 4, that is the very definition of I. An imaginary number right here. And because we took a square root there, we have to put a plus or minus out in front of that. And that plus or minus means we're actually dealing with two different numbers right here. So we expected 4 roots, and we got 1, 2, and because of the plus or minus, this is actually 2 more right here. We got the 4 roots that we were looking for. Now, I do have to warn you guys, since I went ahead and did this on the last problem, I'll do it again as well. If we went to go and graph this right here, we would have this graph crossing the x-axis at 2. Let's see here. I'll go ahead and get started as we're talking about this. Crossing it at 2, crossing it at negative 2. And I do mean crossing because these zeros, these roots, only occur once. So your multiplicity is odd. Now looking right here, this is, just like the last problem, a positive 4th degree equation, guys. So it's going to go up on the left and it's going to go up on the right. Now, we did find 4 roots, but 2 of them right here were imaginary. And imaginary numbers, everybody, if you go back and look at the definition we wrote down for imaginary numbers in section 4.8, it didn't mean much at the time, but it matters now. That definition was numbers that cannot be graphed on the real number line. And this x-axis right here, guys, that is a real number line. Imaginary numbers do not show, in fact, I'm going to write that, do not show up on a graph. They do not show up on a graph. And so what that tells me is, even though this 4th degree polynomial equation has 4 roots, it only is going to have 2 x-intercepts. Why not 4? Because the other 2 roots are imaginary, and imaginary numbers don't show up as x-intercepts. So it is possible that this 4th degree function just kind of looks like a parabola like this. What I think is probably more likely is that it does the weird little y shape that 4th degree functions very often do, but it only crosses the x-axis twice. Later on in this chapter, we'll get a little bit more specific about what that graph might look like, but for now, guys, I'm pretty happy with what we have right there, and I think that's good enough. All right, let's move on to our 4th example. And this is a funny one because a lot of people are going to look at this and think for about, 2 seconds and say, duh, Mr. Fontana. The answer is 1, because if I take 1 to the 3rd power, it equals 1. And that is 100% correct. The only problem with that is this is one of our roots, but we are still missing two others. This is a cubic function, everybody, so I'm looking for a grand total of 3 roots to this. And so far, I think we've only come up with 1. So how are we going to handle this? All right, this is a little bit contradictory to what I've said before, because normally I say if there's only one x in the equation, deal with inverse operations. We would normally try to get rid of a cube with something I don't know if I've taught you guys yet called a cube root, kind of like a square root, but with a 3 out in front. But again, that only gets us the one answer. So let's talk about how we're going to do this one, quote unquote, the right way. Again, get it set equal to 0. So I'll bring that 1 to the other side and get x cubed minus 1 is equal to 0. And in all of the previous problems, what have we tried to do at this point? Factor the expression on the left-hand side. And that's what we're going to do here. First thing we look for is a GCF. No dice. You can't pull anything out from x cubed and 1. So the next thing we're going to do then is start to look for special factoring patterns. And this one right here is unique because our left side is a binomial. Okay, so I guess what I should probably write right here is number 1, we would say look for a GCF, but that didn't get us anywhere. The next thing I would probably write as step 2 is to look for what we would call a special pattern. And that is where we are right now, guys. X cubed, I hope this is obvious, is a perfect cube. And so is 1. If I go back to that list of perfect cubes that we did in the previous video, sure enough, right here, guys, x cubed is equal to 1. And that means that what we're dealing with in this problem, x cubed minus 1, is a difference of cubes binomial right here. So I really want you guys to be aware, whoa, this is a binomial that I'm trying to factor here. And binomials tend to fall into one of these 3 patterns. If they don't, they can't be factored. Like x plus 5, there's nothing you can do with that, all right? But if you are dealing with a binomial that is a sum of cubes, or a difference of cubes, or a difference of squares, it can be factored according to that pattern, and that's what's going on right here. So this one is, ooh, that's an I, is a difference of cubes. So you probably need to go back and look up how to do this one again. A is the cube root of your first term. The cube root of x cubed is just x. And b is the cube root of this number right here. The cube root of 1 is just 1. So here we go, guys. Factoring a difference of cubes, we begin with a binomial. And that binomial is a minus b. Well, our a value is x, our b value is 1, and I said this earlier, whatever this sign is right here, whether it's plus or minus, you just bring it straight down right here. So that is an x minus 1 for the binomial out in front. Now we have a quadratic trinomial that comes next. And how does it begin? With a squared. So if a is x, x squared is just x squared. Now, I said this in the previous video too. Whether you're factoring a sum or a difference of cubes, there's only one minus sign that occurs. Everything else is a plus. We've already used the minus right here. That's how I remember that both of these terms now are going to be positive. Okay, what happens right here? This is the product of a times b. A is x and b is 1, and x times 1 is x. And what happens at the very end? That is b squared. So 1 squared, 1 times 1, is just 1. Now, in the previous problem, I reminded you guys that you're not necessarily done factoring just because you did what you think is the big thing. You got to look to see if you can go further. Well, in this problem here, you can't do anything else with the x minus 1. That's a dead end. You might be tempted to think, wait a minute, that's a quadratic trinomial, and quadratic trinomials very often factor. True, but I wrote a little note for you guys back when we did this stuff in the previous video, and that note is right over here in the middle of the right. The trinomials that you get at the end of factoring either a sum or a difference of cubes never factor. Take that to the bank, everybody. I'm telling you that one right now. So we don't need to bother trying to factor this one any further. Now that's good news and bad news. I would expect you guys to think right now that it's good news because I don't have to do any more factoring. It's going to be bad news for you in a second. Here's what we do. Now that we have completely factored the expression, we use the zero product property. We set, I've been going to purple here, so let me do that. We set x minus 1 equal to 0, bring the 1 to the other side, and we get x equals 1. And that was an answer that a lot of you probably saw 10 minutes ago, maybe not 10, when you looked at this. Sure enough, that is one of your roots. But the second part now comes from taking the second factor, which is x squared, plus x, plus 1, setting that equal to 0, and solving. So now, look at where we are right now, guys. We have a quadratic trinomial set equal to 0. We need to solve that. How do we solve a quadratic trinomial equation? Well, this is chapter 4, and there's 3 methods we learned. The first of which, the best one to try, was factoring. But I told you guys, this quadratic trinomial here is never going to factor. So yeah, that seemed like a cool thing at the time because that meant we were done with the factoring. But it actually kind of stinks because now we have to think about the other 2 methods that we learned in chapter 4 for solving a quadratic equation. So method number 1 was factoring, no dice here. Method number 2 was completing the squares, CTS, if you recall. However, I told you guys repeatedly, completing the square is a great thing to do if 2 things happen. If A is equal to 1, which it is here, and if B were an even number, which it is not. So I would not, as much as I love completing the square, I would not say that that's probably the way to go with this one. So if factoring doesn't work, and if completing the square doesn't work, the quadratic formula, there you go, the quadratic formula is your last resort there, guys, although a lot of you guys prefer to use that sooner than I do. That's what we're going to have to do here. So here we go. X is equal to, and let's see if we remember this from chapter 4, the opposite of b. b is the coefficient of x, which is 1, so the opposite of that is going to be negative 1. Plus or minus the square root of, here we go, b squared, well, we just said b was 1, and 1 squared is just 1, minus 4 times an a value of 1 and a c value of 1 as well, all over 2a, and we just said that a was 1. Boy, there's a lot of 1s in this one. So where does that get us? X is equal to, we've got a negative 1 plus or minus, and I told you guys I really don't mind if you go and put all of this into your calculator at once, but this is one I'm hoping you guys can see right here. We've got 4 times 1, which is 4, and 1 minus 4, is negative 3 all over 2. So what I'm hoping you remember, our discriminant right here, guys, is negative. And that means that we are ending up with 2 imaginary solutions to this particular equation right here. Anytime we're taking the square root of a negative, we're going to be dealing with non-real numbers for our answer. Now, what can we do to clean up the square root of negative 3? Very little, because 3 is a prime number. It doesn't have any perfect square factors other than 1, but the one thing we do, guys, we never leave a negative number in the radicand, underneath the radical. So what we would do here is pull out an I, and then the 3 stays underneath that. So 1 plus or minus I root 3 all over 2. And guys, that's as good as we're going to get. Right here are the second and the third roots to this polynomial equation here. So that is an interesting problem, I think, here, guys, because we looked at it right away, and a lot of you said, ooh, the answer is going to be x equals 1, and that was true, but then we ended up with 2 additional imaginary solutions. So 1 real and 2 imaginary, and that's how we end up with the 3 roots that we were expecting to find right here because this was a cubic equation. So 1 real and 2 imaginary is where we ended up right here. So let me just kind of recap. It seemed like a cool idea when I told you that that quadratic trinomial would not factor. It was actually kind of a bummer because then we had to use another method like the quadratic formula in order to come up with our second and our third roots. I think we actually would have been better off if it had factored, but you know, Some doesn't always work out that way. All right, and I've got one last example I want to do with you guys. This is one I just added here this year for the first time. So let's take a look at this problem right here, guys. I don't think I'm going to need that much space, but okay, just in case. Got it. Whoop. There it is. 3x cubed minus 7x squared plus 24x minus 56. First thing I want you to notice, what's our degree? 3 right here. This is a cubic polynomial, so we should end up with a grand total of 3 roots. But we really don't know how many of them are going to be real, how many of them are going to be imaginary. Well, I kind of know. You guys will learn some of this stuff later on. Step number 1, is there a GCF we can pull out? I don't believe so. I don't think you can pull anything out from 3 and 7 and 24 and 56. No number goes into all 4 of those other than 1. Furthermore, there's no x we can pull out because of the constant term at the end. So nope, GCF got us nowhere. But what I notice, and I hope you do too, we have 4 terms in this polynomial expression here, guys. And when you're dealing with 4 terms, especially when it's cubic or quartic or quintic, something higher there, grouping is the new method we learned at the very beginning of section 5.3. If I go all the way back over here, grouping is the method that we learned where you put parentheses around the first 2 terms right here and the last 2 terms right here, and then you try to pull a GCF out of each one of them and see what you can do. Now, lucky for us, this is the easier type of grouping problem because the middle term here is positive. So we can go right ahead now, guys, and we can group the first 2 terms together, keep that plus in the middle, and then the last 2 terms together. And now we look for a GCF that we can take out from each one of those. So what can we take out from 3x cubed minus 7x squared? Just an x squared. And what does that leave us with? That's going to be a 3x and a minus 7. Got it. Okay, so that's that. Then the plus sign that was right here comes straight down, plus, and now I'm looking for a GCF I can take out of these 2 terms. And out of 24 and 56, I do believe I can divide out an 8. And what would that leave me with in parentheses? 24x divided by 8 would be a 3x, minus 56 divided by 8 would be 7. And all of that is equal to 0. And what I was hoping would happen, happened. I've got 2 big terms. There's one. And here's a second one now being added together, and these 2 terms have a common factor of 3x minus 7. So I'm going to grab that 3x minus 7, and I'm going to pull it all the way out in front of everything here. That's my new GCF, and now I start a new set of parentheses. What's left over from the first term after we take out the 3x minus 7? X squared. This plus comes straight down here now. And what's left from the second term after we yank out the 3x minus 7? That's going to be an 8. And that, you guys, is our factored expression at this point right here. Now, again, I would caution you, it is possible one of these 2 binomials could be factored further. And if you can do that, you should. But no dice here. 3x minus 7 is prime, so is x squared plus 8. So we now invoke the zero product property. We take each factor, go to purple, Mr. Fontana, there we go. We take each factor, 3x minus 7, and set it equal to 0 and solve. Well, this is a weird one. We'd add the 7 on the other side there and get 3x is equal to 7. Then we would divide both sides by 3. And I obviously didn't think real carefully about this one, although maybe it's a good thing that I didn't. I want you guys to know how to handle 7 divided by 3. You do not go to your calculator here and give me a decimal. 7 divided by 3 is 7/3. That's why fractions were invented, you guys, to express ugly quotients in a nice way. So 7/3 is our first root. Now, back up to the top right here, we take the second factor, x squared plus 8, we set that equal to 0 and solve. So again, with just one x right here, I would do inverse operations. I'd bring the 8 to the other side and get x squared equals negative 8, and I would undo a square with a square root. Here and here. Square root of x squared is x. Now the square root of negative 8, that one's going to be interesting here, guys. So what am I going to do? First of all, it's a negative number. So these roots I'm about to come up with are going to be imaginary. Second of all, 8, unlike the, what were we dealing with in the last problem there, guys? A 3, 8 has a perfect square factor other than 1. So I'm going to make the negative 8, I'm going to turn it into a negative 1, times, now what perfect square goes into 8? That would be 4, and then times 2. And I circle my perfect squares. This is my own little preference for how to do this. And I bring out the square roots of those perfect squares. The square root of 4 gives me a 2 that comes out in front. The square root of -1 gives me an I, and this 2 you can't do anything with. It gets stuck under the square root sign, and I end up with a 2i times the square root of 2. But of course, anytime we take a square root, you've got to cram a plus or minus in front of that. And that is as much as you can do to simplify this. So everybody, how many roots did we find? 1 that was real, and then because of the plus or minus, 2 over here that were imaginary, for a grand total of 3 roots. I bring that up because it's so easy, you guys, to forget about the plus or minus. And if you didn't have that there, you would look at this and hopefully you'd think, I have 1 root and a second root, but I'm supposed to get 3. Oh yeah, that's right. I forgot the plus or minus. That's almost always the mistake that people make on problems like this. So on this graph, everybody, we have 3 roots, but since 2 of them are imaginary, this graph would only have 1 x-intercept, because x-intercepts only show up as real roots. Imaginary ones don't actually cross the x-axis. Whew! That is a lot going on right there, guys, in section 5.3. That's a tough one. So let's work hard on that homework right there. Let's see how we do, and let's come in with questions the next day. Good luck, everybody.